Hello, everyone, and welcome for coming to a very outdated talk about C++20. It's already almost 2026, and I'm almost sure everyone here used C++20, right? You just wanted to hear about new stuff. And who actually uses C++20? Nice. That's more than I expected, because usually those big changes in compilers take companies' time. And I just want to show you how good this postmodern C++ is, that you should actually go to your manager and tell him, hey, we want C++20. It will make our productivity better and our life much, much easier. So just because I asked you the question about who actually uses C++20, this is the standard survey that was done this year. And as you can see, at least most of the people are already using C++17. That's a huge progress. But C++20 is still lagging behind. Only 43% of all people that use C++ actually get to experience C++20. This is horrible, in my opinion. People are lagging behind and not using newer and safer things that are actually important for the language. We just had a wonderful talk by Daniela. She talked about these things, and C++20 gives you a lot of those as well. So a few words about me. I'm Dathskovsky. I'm a director of software engineering in ScyllaDB. ScyllaDB is a blazing fast database that gives you low latency, is distributed. We are actually using some parts of C++26 already because we're pushing forward into the future. And we can give you a lot with your databases if you need something that is really blazingly fast. I have a LinkedIn page that is really, really active with C++ stuff. I got some riddles there, so not everyone likes riddles. Beware. I have a blog that I maintain that's called CPP Next, and there I write more about C++ stuff, things that I cannot just write in a post. And for a year now, a little bit more, I have a YouTube channel where I break down the things in videos and try to teach C++ in a better way, because in a video it's almost always better. But I can tell you that making videos is not easy, and I don't have enough time for that, so I really try to do it once or in a month or 2 months. Okay, so what can you expect from this talk? Usually my talks involve crazy templates and crazy stuff like that I'm showing here. And because I'm a performance guy and I'm a compiler writer, I always tend to show assembler code. But some people think it's too hard, some people say it's too dense, some people think it's pretty cool and pretty fun and like those kinds of talks. I can assure you this time it's going to be just a fun talk about C++ and how C++20 makes our life easier. So I just wanted to shout out, yesterday I came very, very late, and I could see just one talk, and the talk was by Bogoslav, and he actually mentioned a lot of the things that we're going to talk about today, and he did it in a very nice way, because he's teaching, and he's teaching how to use modern and postmodern C++ to create compilers in a safer and better way. So I really enjoyed the talk. You should see it as well, in my opinion. Let's start. C++20 is huge. The changes that were introduced were enormous. We cannot cover all of them. I cherry-picked a lot of things for you, but we will not speak about everything, maybe 50%. Another important thing to get out of the system is I'm not going to speak about the Big Four. There was so many different talks about the Big Four that we don't have to talk about them again. I will just mention them for a second, and then we will go to the smaller stuff that are not less important than the Big Four, and sometimes I think are even more important than that. So let's start with concepts. Concepts is a great way to write generic functions. It really makes your code, if you are writing generic code, easier. Here I show an example of how not to write generic code and not to write concepts. I call this smile, but it will make your coworkers cry. If you want to hear more about how we advanced from templates to concepts, I have a talk from C++ Now, from C++ Now 2023, where I explain and go to depth about those things, so you can catch it out later. Ranges. Ranges is a great way to represent functional code in C++. It gives us a lot of abilities. When you write ranges, you need to take into mind performance. So when ranges started, performance was not that great. Right now, performance is usually the same or a little bit worse. But still, if you get sometimes when you get readability and maintainability, it's a little bit better than just writing what what I'm showing here. Before ranges, to do something really simple like we are doing here, we had to create a lot of code. So all we are doing here is taking iota and reserving 20 numbers, and then copying if the numbers are odd or even, or are odd, and then we are reversing them, and it all takes a lot of code. With ranges, all you need to do is this. 4 lines of code. Does the same thing. I do have to say that I used views here. And views are problematic, because views are like pointers to something. So what this code does is basically taking references and doing nothing. The first time that actually something starts to run behind the scenes, it's when we are printing it, because only then the activation begins. So if something gets out of scope, that's a problem. That's an undefined behavior that may cause trouble. So views, sometimes people tell they are busted, but you still can use them if you know what you're doing. Another good talk from CPP Now in 2024 was by Roy Barkan. He talks about ranges and all the things and all the algorithms that were added in C++20 and C++23, and how to create better algorithms by yourself. So you can actually plug in your own ranges in and do a lot of stuff with them. In C++23, you got many, many things. So right now, we can write as if we are in functional programming languages like Haskell, almost Haskell. Modules is a great idea that declutters the code and makes compilation easier and faster. The problem with modules that until last year, we couldn't use them. Right now, we can use them with modern CMake, but it's still lacking a lot of things, and people actually don't use it. I'm always running after the latest C++ standard. I never got to use those, because they're still lacking. If you want to learn more about how modern CMake deals with modules, you can see this video by Bert Brown and Bill Hoffman. Well, Bill Hoffman is the CEO of CMake. He's the inventor of CMake, but he's the CEO of VTK. Kitwer, sorry. And they're explaining how they got to a position where they actually started implementation. Each year, when I go to CPPCon, I speak with Bill, and he's saying, yes, we are getting a little bit closer, but we still need a lot of time. So there are many formats and many things that were not actually defined in the standard, and they're defining them now and creating that. Hopefully, we will have modules soon. Coroutines. Coroutines is a huge thing that was added in C++20. It gives you the ability to actually write asynchronous code if you don't want to do it with threads. You can do everything on the same thread as if it's fibers, but those are coroutines that have a state. The only problem, in my opinion, with C++20 that the implementation is really hard on the user. The interface is hard. You have to know a lot of rules, and you have to create many, many, many structures and structures inside structures. We will not go into that, but Andre Weiss had a great talk in CPPCon 2022 about coroutines and exactly how to create them. So he made it a little bit easier, but still, you have to practice to understand those things. And now, let's get to the smaller things, what we actually want to speak about right now and today. So let's start with abbreviative function templates. Until today, if we want to create a function template, we have to write the template itself. We have to say we have the type name T, type name u, and then use them inside the function. Now, with C++20, we don't have to do that. The compiler does it for us. So basically, we can use the auto inside regular functions. Behind the scenes, the auto will transfer itself into a template, but we don't have to write it. Auto is basically the weakest concept of them all. Auto says, I can receive any type I want. Of course, that can be a little bit problematic because we don't want to use any type. We want to use sometimes specific types. We want to concrete the type a little bit. So in this example, we need to create a concept. We're creating a concept that means that each one of the types that it receives, T must be an integral type. It cannot be anything else. And then to use it, to constrain the auto, we have to write the concept before the auto. So here we are saying the doThing function will take an integral type and an integral type. Inside the function, we are using something from C++14 that's called common type T. It will take the most common type, and then it will return T plus U, because it will be implicitly converted to this type. We could do it without the trailing return, but I think it's a safer way to do that because there will not be surprises here. One of the problems that we have with abbreviative functions is that we don't have homogeneity. When we had templates, we could just say, OK, we have a function that is templated on some type, one type only. We're returning this type, and we're receiving two parameters with the same type. Pretty easy. But now, if we're saying it with auto, auto can be anything. It can be any type. Even if we're saying it with a concept, we're still not defining it entirely. We're saying A can be anything we want, and then we're using decal type on A just to fix it. That's clutter. That means that A is something, and then B has to be of the same type of A. But there's a problem here. The problem is that A might be a reference. So maybe we don't want B to be a reference. Maybe we don't want B to be a constant. But auto will take all the type in. So that's a little bit problematic. It will work, but sometimes it won't. A very naive approach to that is to say, OK, we have a trait from C++14 called decay. Decay takes the type and decaying it to the most basic type there is. That means A can be whatever it wants. I will get the actual type behind A. That will work, but still it has some problems with it. To understand what the problems with decay are, and those are inherited problems, decay will decay arrays to pointers. Thank you, C. That's all because of C. So arrays in C really want to be pointers. That's all their purpose in life. We want to be pointers, and we don't want to be safe. And function pointers are basically functions. So C tells us that, well, all function object likes are function pointers. We don't care about anything else. Again, we don't want to be safe. Even when we look at ABI from C, there are like no types there. Everything's fine. Everything will be fine. I don't have the dog here, but you can imagine her. So because of that, if we will do something like that, we will create an array, and then we will ask with same S is a concept that checks if types are exactly the same, and we are doing it with decal type for A, and the decay type for A, we will get an error, and the error will tell us exactly that. One is an array, and one is a pointer. Those are not the same types. Same for functions. Here I'm defining a function, and the decay just makes me use a function pointer that I don't want. The real solution for that before C++20 was to peel the reference and then remove the constant and the volatile from the type itself. But it's cluttered. There's a lot of writing to do here and a lot of templates, and I'm not sure that I want to write all those things. The real solution from C++20 is remove severe FT. So it's not a huge thing, but it just makes your life a little bit easier. It's a little bit easier to use this. It's shorter, and it's safer. It does exactly what you want, and it does exactly what you need. You don't need to guess that maybe it will be dedicated to something that you didn't expect it to be. Now let's get back to language features. Designated initializers. Well, this is something that I was waiting for a long, long time. In C, regular C, we had the opportunity to initialize structs with the member names. That was much, much better than the things that we had in C++, where we just needed to do everything without names, and we couldn't skip. Right now, we still need to do everything by order, but at least we can skip parameters. Here you can see that if we are skipping Z, it will be just initialized to vector of zeros, empty vector, sorry. And if we are reversing the occurrences of those members, that will not work, that will be an error, but we can skip even the middle one, and it will be just set to be 0.0. It makes code readable, more readable, and easier to maintain. In my opinion, it's much, much better than just using aggregations. There are plenty of rules. Of course, with C++, you cannot live without rules. But the most important rules are that you cannot have base classes, you cannot inherit, you cannot have virtual functions, and you cannot have a constructors. So because if you have a constructor, you cannot be an aggregator type. Ranged for initializers. This is a simple example of what I want to do. So here I'm saying I want to iterate over an array, but I want to do it in a safe way. So ranged fors are much better than regular loops. And because of that, I'm initializing an integer called I before the loop. And then I'm going and looping over all the elements inside the container and printing the index, plus then I'm printing the value as well. The problem here, in my opinion, is I leaves too much. I don't need I after this loop. I just needed it for this printing. Why do I need to make it live for a long, long time? It will just clutter the code. Your symbols will be everywhere. I will stay alive for as long as the function lives, or as long as if you created it inside the main, it will live forever. Of course, we can go to the old way and do it with index-based loops, but those are dangerous. You can always do undefined behavior with those. You can step outside your boundaries. You can make a lot of silly mistakes that will explode your code. So we don't want those. In C++20, we can initialize values inside for loops. In C++17, we could do it for ifs, and now we finally can do it inside fors. So in this example, we are initializing the I inside the loop. We are looping with for each, range-based for, and printing the same thing. And this is safe. And I will not live after this loop. So when the loop ends, I will disappear. Now let's go to the moon with Linux Penguin and some starships. Who hates boilerplate code? Raise your hands. Is there someone that, some people didn't raise their hands, so they love boilerplate, like writing the same things over and over? So when we wanted to create a class in the old days, before C++20, and we wanted this class to have operators, we had to write a lot of boilerplate code. Basically, all those operators that we see here in this class S, they are boring. They're doing nothing. Why the compiler doesn't create it for us? Why the language doesn't create it for us? Of course, if we will use them, we will have only those operators, but there are some operators that I didn't implement it, and we will not get them for free. So basically, each time that you wanted to create a new class, for example, this kind of vector here, and you wanted to create all the operations that you needed because those are things that are mathematical, and you want to put it in mathematical functions, you had to create tons of boilerplate code. With C++20, it became a little bit easier, Because you got default comparison operator. So we will get to the starship soon, but if you didn't want to use starship operator, at least you would get the operator equals as a default. So you don't need to write it. But that's not good enough. We want to use the starship operator. The starship operator removes the boilerplate code dramatically. What is the starship operator? Starship operator is a three-way comparison way. That means it does all the comparison at the same time. It may return three types. It returns strong ordering. Strong ordering means, well, sorry, I'm just jumping over the shark. We will get there soon. And it generates all the simple operator cases. So instead of writing all the boilerplate code that we've seen before, all I need to write is starship operator, const equal default. Done. We have removed tons of code, and it just works. So again, the same example, but now, because I wrote it with the starship operator, I get all the comparison for free. And they work. They actually work. They do the correct thing. So what are those orderings? Strong ordering denotes that if we have two numbers, A and B, and we have one function, if we will use function with A and the function will be, the values will be the same. This is simple linear algebra. And it also denotes that A must be one of the three things: smaller than B, equal to B, or greater than B. So this is good for strong numbers, integers, floating points, not all floating points, we will get there, but this is good for real numbers. We have weak ordering. Weak ordering is almost exactly the same as strong, but it says that there might be a function where FA is not equal to FB. Where do you think something like that may come in handy? Anyone knows? Yes? Almost. We will get to not a number soon, but good guess. This one is good for example. A very, very simple example for this usage is strings that don't have the same capacity. Like, say, we have hello with capital letter and hello without a capital letter. They are equivalent, but if you look at them in a mathematical way, they are not. So we can say in our starship operator that those are equal and return weak ordering. And now for the nonce. Basically here, if you want to use something with nonce or infinities, you need to use partial ordering. So partial ordering says, again, almost the same thing as weak ordering. There might be a function where they will be different, but they also are saying that there might be sometimes that the rules for less than, equal, or more than, or greater than are not applied. So that's exactly infinity. Infinity and infinity. Is infinity greater than infinity? No. An important thing is that if you want to use partial ordering, you have to include the compare header. That's a weird rule, but it's there. So here's an example. As I said, this thing is a vector, and we cannot just use the default operations there. We will create a normal starship operator for it, and this is how we do it. It's pretty simple. We're creating a simple lambda that will do the comparison, because that will calculate the magnitude. Why? Because vectors are equivalent by magnitude, not just the numbers inside it, not just the members. So we will take the magnitude from this, we will take the magnitude from other, we will check if they're less than, equal to, or greater than, and return the strong ordering that we actually need. That's all we need to do here, just return the strong ordering. Then an important part is to create an equal operator, and from the equal operator and the starship operator, all the regular Boolean operators will be created for you. And the equal operator is pretty simple as well. So basically, we need to say, like, If the starship returns strong ordering equal, then they are equal. That's it. And if we will use the same code that we used before, we still get all the functions generated. It's still simple. You can create your own classes. You can create your own code, your own complex code. And all the boilerplate, almost all the boilerplate will be gone. And it's super, super important. When in my previous company, when we actually got C++20, I removed more than 4,000 lines of boilerplate code just because of operator Starship operator, sorry. Signed integer rules. So this is funny. Until C++20, each compiler could decide for its own. The signed integers could be signed and magnitude, 1's complement, or 2's complement. If you use one compiler, it would be 1 complement. If you use the second compiler, it would be 2 complement. That means migrating from compiler to compiler would be a compiler hell. But now, with C++20, it's defined in the standard. So compilers cannot do that anymore. They're just saying, if you are using signed integer, do it with 2's complement, nothing else, which is really important. No unique address. Another small thing, but it's really, really good for your performance if you need to save space and you need to do something with your program that needs to be compacted, let's say it like that. So here in this example, we have a struct called placeholder. Placeholder is an empty struct. As you know, in C++, if we are creating even an empty struct, it will have at least 1 byte of size, because we need an address for it. We cannot have something that doesn't have an address. Then we are creating struct S1 with 32 bits unsigned integer x and a placeholder p. Then we have struct S2 with the same member x, but then before p, we're saying no unique address. Basically, when we're saying no unique address to this thing, we're telling the compiler x and p can share the same address because p will not be used. And if we will try to print the sizes, we can see that placeholder size is 1, as I said. This is on Clang. On GCC, it will be the same. On Microsoft, I cannot promise anything. Their compiler is horrible. The size of S1 is 8, and the size of S2 is 4. Because we didn't use no address and we used the placeholder, it gave it 4 bytes, even though it just needed 1 byte. But it gave it 8 bytes because it needed to be aligned to 64 bits. And to 32 bits. And here in line 130, we just have 4 because it's aligned. We don't need anything else. And we are told the compiler, you can compact this. So this can save you a lot of code. If you think about things that you are doing with sending messages on network or things like that, this is really useful. What do you think will happen here? So we have 2 placeholders. Will this work? Will we still see just 4 bytes? Who thinks yes? Hands up. 1 person. Who thinks no? More people, but I guess most of the people don't exactly know. So the problem is here that we will still get 8. And the problem is that we have 2 placeholders. Because we have 2 placeholders, they have exactly the same type. And there's a rule in C++ that says if we have exactly the same type, they cannot share the same address. So we saved one of the placeholders, but we couldn't save the other. Of course, if you will do another placeholder that's called empty, you can still do that. But you can do it in a simpler way and just use templated placeholder. So if we are just giving it indexes, and we can use those for struct that need more than 1 placeholder for something else that we will use in the future. Lambdas got much, much better. So this code is one of the few things that you will see here that has a lot of ellipses. And lambdas love ellipses in C++20. Since C++20, we can actually capture variadic parameters into a lambda. So until then, we couldn't do that. We needed to push them as parameters into the function. Right now, we don't have to do that anymore. We can do it like that. You can see that I'm passing all the parameters, all the variadic package, into the lambda, into something, a new variadic package called x. But of course, we had to do something that will confuse the programmer, and the ellipsis is on the front of the x and not on the back of the x. So just to be sure of. And then you just do a simple fold expression and sum everything up. Lambdas also got generic. Until C++20, we could use auto on our lambdas. That means it would be initially templated, implicitly templated, sorry. But since C++20, we can actually specify that the lambdas that we want to create needs to be templated. So here we see code that is mixed in with regular templation and auto, a concept that will be used with anything. Why is it good? Before C++20, if we wanted to go over variadic package, we had to do something like that. So we have a function that is templated on indexes, a variadic pack of indexes, and types. The first parameter that it receives is just a type that's called index sequence. Index sequence was created in C++11, and it just looks at the size and creates a variadic pack of integers for you. But the good thing here is that we said that the ISs from the index sequence are just indexes that we are using as non-template parameters. Then we are pushing the actual types or the actual data as variadic pack of universal references. And then we are returning, for each index that was pushed to this function, we are returning the type, and we are actually summing it up inside this function. Then we had to create the base function for it that's called sum first 5. We are taking the size of the variadic package, we're pushing it into sum n first, and it will just sum the 5 parameters. So it's a little bit dirty, in my opinion. You had to create a special function, then you need to push the make index sequence into it, and all this done just to push the make index sequence into it. That's all. Before C++20, you couldn't do it with lambdas. But now, with C++20, it got much, much easier for us. We can do everything in the same function. So we are creating the sum first 5, and we are creating a lambda. The lambda takes the parameters, all the data that it needs as a tuple of a's, and it's templated on the indexes that we wanted. Then we have the parameter that we are sending to the lambda. The parameter itself is defined as the index sequence that we want to use. And we are returning exactly the same thing that we returned before. The thing here is that we are creating the lambda and starting it, basically making it run in the same time. So we're in the same place we created the function, and we call the function with the make index sequence exactly as the first one. But here it's better, because you don't need to create a free function or a function inside your class that will not be used for anything else besides something that you need for this functionality. So it makes things a little much better, in my opinion, because everything is concreted and it's inside the same place, and it's much easier to read and to understand. Well, you have to get used to all the ellipses and all the things here. And of course, when we run it, it does exactly the same thing. Constant evaluation got better as well. So until C++20, we got const expression. Const expression is great. It does a lot of things. But in C++20, we got constant evaluated runtime. Constant evaluation means that we run in compile time. That's it. Const expression can run in runtime. So here, if we are creating a function that's called mult1, which is const eval, and then we want to run it inside a function that is constexpr, the compiler will tell you, I cannot do this, because we are transferring into constexpr a parameter that may be not available in compile time. And that means that we cannot evaluate it. If it had no parameters, maybe it would allow it to run. But right now, we cannot do that. If we will just change mul2 to be consteval, that's not a problem, because the compiler knows that mul2 will run only in compile time. Not before, not after, not in runtime. Another interesting thing that was added to C++20 when it comes to constant initialization and constant runtime is constinit. Constinit is different than constexpr parameter because constinit tells the compiler this parameter has to be initialized in compile time, but it's not constant. So here you can see I'm initializing something in compile time. It is using the mult1 function, which is consteval, and that means that it must be run in compile time. And then we are adding to mult20, and that's fine. We will just print 220. So it's saving you a little bit of time if you know how to initiate something and you don't need to do it during runtime. We can actually create heap data with C++20 in consteval functions or constant expression functions. That's huge. Basically, you can use the memory from the compiler runtime to create something inside the compiler's heap to use it, but the only thing that you need to remember is that you have to delete it. If you don't delete it, you will get a note from the compiler that you forgot to do that. And basically, it's an error. It's not just a note. I just wanted to show the note because it's self-explanatory. It says, hey, you perform an allocation, please delete it. And as we spoke in the previous session with Daniela, constant evaluation is great. It makes you know exactly what you're doing, and it will alarm. It will tell you forgot something. It will tell you that you have undefined behavior. So that's, if you can use more constant expression functions, that is great. NTTP, non-template type parameters. They got really, really relaxed in C++20. So before C++20, the only non-template type parameters that you could use, it's integers. That's it. Integral types. You couldn't use anything else. You couldn't even use a simple type like a float. It was not NTTP. But now, with C++20, it's all open. You can use floats, you can use your own classes, and in this example, I wanted to illustrate how you create a fixed string, which I think is one of the common things that were done, the first thing that C++20 arrived. And I'm doing a lot with those fixed strings. I'm creating compile time SQL algorithms. So that's worked pretty good. So here you can just see we have a class that defines a string that will be compile time held. And everything here is const expression because I want it to be in compile time. And of course, I added the spaceship operator here because it's cool. And it's const expression. So afterwards, we need to give the delegator. Basically, we want to help the compiler that if he will see that we are calling fixed string with an array of characters, it will know that we actually want to call fixed string with size -1. Then we are creating an aliasing, user aliasing, that helps us to create fixed strings. So if you will use this fs functionality on a string, or basically an array of characters, you will get a fixed string from it. So it's really easy to use it here. And the last one, in line 202, you get last letter. So here we are just using the fixed string as we developed it. And if we will print with hello underline fs, we will get O, because the last character is O. So it's easy, it's easier to do. And as you've seen, we have provided the fixed string as NTTP to all the templates. That's what makes it possible. It's much easier. Before, if you wanted to do something like that, you would have to send the whole array of strings, or the whole array of characters, into the template, and then run over the characters and do horrible things. Right now, you don't have to do it because you have all the power in your hands to do good template metaprogramming, and easier to read, in my opinion. Explicit. Explicit got better as well. So before C++20, if you wrote explicit, it meant that the function is explicit. That's it. Here, from C++20, you can do explicit and tell it, be explicit only if something happens. So again, if you're doing template metaprogramming, generic programming, this is really great. Here we have an example that receives a number and says that the constructor will be explicit if and only if this value is even. If the value is not even, I don't mind implicit conversion. And here we have an example how to use it. If we will use it with foo with 3, we will be implicitly converted. If we will use it with foo with 2, it will tell us we cannot do it because we have to be explicit. We have to actually push s and not a regular integer. Const expression polymorphism. In my opinion, this is one of the best things that was added in C++20. Until C++20, if you wanted to do something that looks similar to polymorphism, you had to do curious recurrent template pattern, which is horrible, and people don't understand it, and each time people are seeing it, it's harder for them. But hopefully, we don't have to do it. And tomorrow we will speak about C++23, where I will talk about self-deducing this. This will help even more. So this pattern of CRTP is almost not needed anymore. So in this example, it's really simple. We have an animal class, which is the base class. All we have to do to create a const expression polymorphism is just to add virtual const expression. That's it. It tells the compiler those functions are virtual, as if they have virtual table in them. We have a struct that is a duck that inherits from animal, and it implements number of legs with 2. And we have a cat, which is an animal, and it implements the number of legs with 4. Pretty simple. It looks as if it's a regular code that you already know how to write with polymorphism. To use it, inside main, we have to create duck and we have to create cat. Then we are passing an array of animal pointers with the pointers to duck and cat on the stack to a function called countLegs. And the function that called countLegs is just a function that receives a container with animal pointers, and it goes over the animal pointers and sums the number of legs up. Pretty simple. Again, the code doesn't look like something that you have done for constant time expressions or something like that. It looks like regular code that you have written before, even in C++98. We have done almost all the language features. There are many more, but we are going to library features now. So, safer integers. I have mentioned that integers had many, many problems before C++20. They still do have problems, other than just not using the correct signed integers or the same signed integers. Here we have a simple function that receives 2 parameters that can be anything, and it just wants to return the maximum between those 2 parameters. It's a very, very silly way to implement max, but it's something that can be done like this. So if x is less than y, then we return y. If not, we return x. What will happen if we will provide -10 and 20 unsigned long to it? What we will get back? -10 or 20? -10. Who thinks -10? Okay. Who thinks 20? And it's -10. Why is it -10? Because C++ and C has many, many implicit conversion rules. That means when the compiler sees that it got signed integer and unsigned integer with the same size, the first thing it will do, it will turn the signed integer into a stronger type, which is unsigned integer. And minus 10 in unsigned integer is much larger number than 20. So this is one of the problems that we get here. But with C++20, we got the ability to use safer functions. We got all the functions that will do all the work that we need for typing and will give you the actual results that we were expecting. So if we will just change the same functionality, but we will change the function to a safe comparison function with x and y, and we will use the same thing, we will get 20. Because inside the functions, they're checking the types, if something is signed or unsigned, and doing the correct things with them. And if you want to learn more about it, I had a talk in CPP North last year about to int or not to int, where I speak about all the pitfalls with integers, and there are a lot of faults with integers, and how to fix them and how to use them in a better way. Heterogeneous lookup. So this is something that we had in C++14 for order containers. Who knows what heterogeneous lookup is? Not many people, so that's good. So heterogeneous lookup just gives you a little bit more performance, around 20% more performance, and I will explain why. Here we have a map of strings and ints. And we have very, very long strings inside the map, and it maps it into small integers. Then we want to use that. So we are creating a long string, which is just char pointer, and what happens behind the scene is this thing needs to be allocated on the memory, because this thing needs to become a string. The key is a string inside the map. We cannot do it with a regular char pointer. So we had to do it, and I used the long strings for an example because long strings actually allocate on the heap. We don't have small string optimization here. To fix it, all we had to do is to provide std_less without any parameters inside them. Why? Because std_less with no parameters inside them will create a special functionality for you that will make the types transparent. And then, when you will use it, it will not convert the strings into an actual string. So you can use it with a string view, you can use it with char pointer, it will just not allocate. It will do the work of the less for you without doing those things. So you save a lot of time, a lot of performance. Now, in C++20, all we had to do is to wait 6 years, and we got the same thing for unordered containers. To do it for an unordered container, it's a little bit more complicated because you have to create your own hash function. So here we are creating our own hash function, and we are creating the 3 functionalities to do the conversion to the hash from the string. So if we will use that, we will get the functionality we had for ordered containers. And the most important part here is line number 501. You remember I said that it defines something that is transparent? Here we are defining by ourselves that is transparent is something that is part of this struct. We must define it. And then to use it, you can just use it like that. You're providing your hash into the unordered map, and you have to provide the stud equal without parameters to it as well, because stud equals without parameter is a transparent functionality. Spans. Spans are cool. Span is basically, if you're Python users, you know that you can look at the slices of an array. Span gives you the same possibilities in C++. And it's really easy to use. And the only thing you need to remember that span is not containing anything. Span is just a view into your array or into your container. And another problem, well, it's not a problem, it's a definition. Spans have to be continuous. They work only on continuous containers. To show you an example how to use it and how it makes your code a little bit easier, I need to explain about trees. Who remember university balanced trees versus unbalanced trees? Ooh, people remember. So an unbalanced tree is pretty simple. It means that one of the sides is a little bit deeper than the other. A little bit deeper is basically, even if we have two, the depth is larger by 2, we have a problem, and we have an unbalanced tree. To create it, we have a function that we have just a struct that is a node that creates the node itself, and we have unique pointers to left and right, just to create a tree. And then to use it, let's say that we have a functionality that someone asked us during the interview to create a function that balances a tree. Yes, we had to do some work before that, and we had to traverse the tree and create an ordered vector from it. But here I'm just showing the function that goes on that vector that we already got. So instead, in create tree, instead of using a vector, we are saying we are providing a span of integers, not a vector of integers. Then we are creating a simple function just because we need to make boundaries, and we are saying, okay, we are receiving the size that we have now, and we are receiving the span that we have. If size got smaller in the recursion than 0, or it's equal to 0, we're returning an empty span. If it's something that is larger, we can just return the span itself. We have the stop of the recursion that says if the span is empty, we are returning a null pointer. And then instead of doing all mathematical functionalities and doing all the problems, the small problems with indexing inside here, we can just do this. We're converting the middle, we're taking the middle from it, we're creating a unique pointer with middle as root, and then we're calling the functionality for left and for right. And that's how we are balancing the tree. It's pretty easy. It removes a lot of problems inside codes like that, and I'm sure that if you write this code in a code interview, you will get some points if the interviewer knows C++20. Bit header. So bit header is a great thing that was introduced in C++20. It has many, many functionalities that we have to implement by ourselves before. It has a lot of bit and byte operation that can make your life a lot easier. And the most important things, everything is constexpr. Here's a very, very good example. If someone used networking and they know basically that you have small Indian and little Indian and big Indian. Before we had C++20 and we had the bit header, we had to implement it by ourselves. So we created an enum class, and then we had to create a crazy function that takes a number that is 16 bits, then it does re-entropy cast that is horrible for something that is an array of 8 bits and 8 bits, and then it looks if something is 1 or not. There's a lot to understand here. With C++20, all you need to do is to use the native thing that we got inside there. So you can basically ask in a system, hey system, what you're operating on. And all you need to do is that. That is readable. That is human readable. You can understand that. You don't need to understand crazy bit tricks and crazy stuff that only people that know embedded can be good at. Another good example is pop count. And I want to show it just because we have bit fields here. So we have 2 bit fields, and pop count is an algorithm that is really important if you are doing some embedded, that counts the number of bits that are 1 inside your number. Here we're using the pop count, and we actually had to implement the pop count by ourselves. We don't need to do it anymore, but it's pretty easy. You're going over the value, you're ending it with 1. That means if the bit right there is 1, then we are adding to the resolution. If not, we are just pushing it, shifting it left. And then to use it, we need to do something like that. But here, I'm showing the pop count from the bit header itself. We don't need to implement anything, and it's const expression. Basically, we have created a struct that is constexpr. We have created a pop count, our own pop count that we implemented before, and we implemented the pop count from standard, and we got the same numbers. So it's easy, it's constexpr, and it's great. Basically, all of C++20 makes us lazier programmers, but being lazy, it's not a bad thing, in my opinion. Bitcast is a very important thing. Bitcast, if you're doing embedded, sometimes you need to transfer types from one type to another. And it's really, really important to do it in a safe way. I mentioned that re-entry cost is horrible. Re-entry cost is horrible. Bitcost is the way to go here because it's well-defined. So it makes us a little bit safer, lazy and safe. And if you want to know more about re-entry cost shenanigans, I had a keynote in CPP Nord this year about all the things that re-entry cost does, and about one of my libraries that I'm developing that's called safecasting. You can take the safecasting from here. Source location. Source location is has a great value for logging. You can debug in a better way. So until then, we had to do a lot of loops and do the source location by ourselves and had to use macros. Here, we don't have to do it because we are getting it from the standard itself. Here, in this example, I'm showing how to use source location, how to push it into your logging functionality, and this will append the location inside the code with your formatter. As easy as that, and it will make your logs much easier to read without a lot of work to do there. Better threading, and this is a huge part of C++20. We have much, much better memory module. We have a lot of defined structs and things that the standards give us, and it's easier to use, and it's easier to create algorithms with them. So for example, we have a JThread. JThread is wonderful because you don't need to think about joining a thread anymore. So how many people here had a problem and they forgot to join the thread and then the application crashed when it stopped? Thank you. Now you don't need to worry about that. And it has more functionality like stop source that you don't need to reinvent the wheel because you can ask the thread to stop working. Here we have an example of something, another thing that we got. It is semaphore. I don't have a lot of time to walk over those, but semaphore is basically, we waited for semaphore until C++20. We had just the POSIX semaphore. It's really easy to use. Here you can see that we have a person speak functionality. Here I'm using binary semaphore, but you can use counting semaphore. It can count to any number that you want. And we are basically synchronizing the two people when they're speaking. We're acquiring all semaphores at the start. Then we are releasing the semaphores when the JThreads were created. When they were created, they are not running because they got to the acquire and they cannot acquire it. Then we are releasing them, and if we will print it, we will get the order that we wanted. Stop source location, as I mentioned, JThreads have stop source in them. So until now, you had to recreate the wheels with your own booleans and signals, and you had to send them between threads. You don't have to do that anymore because each JThread has a stop source in it. So here we have almost the same function with stop speaking function that is basically saying, please speak, please stop, please stop. And all you had to do is to go into the threads themselves and take the get stop source from inside them. And we got exactly what we wanted. Person 2 and then person 1, then goodbye. Latch. Latch is a great algorithmic advantage as well because latch is something that works. All threads are getting to it. They're decreasing something, and then they need to wait afterwards in the wait. So until everything is decreased, if some other thread is waiting on the latch, it couldn't run until we get to a full stop. That means until all threads decrease the latch until 0. Only when something is decreased to 0, then the other thread is released. So here you can see that even here, we had a pretty easy functionality to create something that is synchronized between each other. We have people that are doing a job, then someone tells them go home, and they are starting going home, one by one. Barrier. Barrier, the only difference between barrier and a latch is that barrier can be refired. So barrier is something that works a little bit different because you can see it arrives and waits. Unlike latch that is decreasing and then you have to stop it with something, it arrives to a point, it waits for it, and only if someone actually releases it, only then we can start it again. What releases it? It's an on-completion function. When something is done, it's called an on-completion function. Here we have just a small lambda, and this lambda has a state inside it. In this state, we are just saying, if it's the start, we are saying go home. If it's the second time we are calling this function, we are done. And as you can see, this is pretty clear, and we have synchronized our code in a very simple way and done it in short amount of lines, small amount of lines, and done something that would take us in older C++ a lot of effort. If you want to know more about that, I had a C++24 talk about memory barriers and how memory is actually working in C++ since 11 until today. I think it's a really good talk. So in conclusion, C++20 makes us happy, at least me, because my life is much easier since I got to C++20. Now I'm using C++23 and 26 a little bit, and it's much easier. If you're doing insane things with templates, your life will be easier. If you're not doing insane things with templates, you have so much functionality for everyone that makes everything much easier and simpler and easy to maintain and to read. We will not do that, and with that, we are finished. Thank you, everyone. Anyone have questions? Online?
Right.
Okay.
We have time for one question, so take an online question. So Ayel asks, if I want to make sure that a variable of a class is constructed at compile time, should I mark its constructor as consteval or the variables as constinit?
You should do the constructor as constexpr. That's how you do it. So when you will run it, you're basically saying that this class can be created on compile time or on runtime. And then when it's created, if you are creating it inside a constant evaluated zone, it will be constant evaluated. So basically, when you're creating it and it has a const expression constructor, you can use constinit to create the class, and it will make it be constexpr. Or if you just write constexpr, it will make it constexpr as well.
Thank you.
That's it. Thank you.
Thank you.